All right. So section R1, units of measurement. There are 7 SI units of measure. SI stands for the System International, and these are what the science field, all sciences have decided upon as the main units of measure. You have any number is nothing by itself. If I just say I'm 3, what could that mean? It could mean I'm 3 days old, I'm 3 years old, I'm 3 years into my job, I'm 3 feet tall, I'm 3 pounds or kilograms or whatever, or I'm 3 days away from doing this test I have to do, or whatever. A number is meaningless. You need to have units. And so those units have to be standardized in a way that anyone around the world can read it and understand what it means. So we have these 7: mass, length, time, temperature, mass, length, time, temperature, electric current, the amount of substance, and luminous intensity. I'm going to go over the true scientific definition of each of these, but also keep in mind the symbols used to signify each of those units of measure. Mass is measured in kilograms, length is measured in meters, time is measured in seconds, temperature is measured in kelvins, and electric current is measured in amps. The amount of substance is measured in the mole, and the luminous intensity is measured in candelas. These 3, the kilogram, the Kelvin, the mole, those are the 3 main units of measure that will be used in this class or by any chemist in general. So the meter is defined as the length of the path traveled by light in a vacuum during a time interval of 1, essentially 300 millionth of a second. That's obviously a very, very, very tiny frame of time, but light in a vacuum will travel 1 meter in that amount of time. And the reason that it has to be defined by light is that really the original definition of the meter was 1/10,000th the distance from the North Pole to the equator. And the problem with that is that Earth is not a perfect sphere, so different parts of Earth would have different distances, and so it doesn't really work. And the size of Earth is always changing, actually, because there's always meteors bombarding Earth, and so it's actually growing, and so this wouldn't work forever. But the speed of light never changes in a vacuum, so this is something absolute and definite, that light will travel that far in that amount of time. The second is defined as the duration of 9,192,000,000 and so on periods of the radiation corresponding to the transition between 2 hyperfine levels of the ground state of the cesium-133 atom. Again, this might seem weird. You all intuitively know what a second is, but in science there has to be a definite, unchanging definition of it, and the problem is that time actually is relative, and we can thank Albert Einstein for that idea. You may not know what it means, but I'll try to explain it here. If you take 2 clocks and you synchronize them together, and you leave one on Earth, and you take the other one and you put it with an astronaut, and you send it up into space, and you let it stay up in space for an extended period of time, and then bring it back down, the clocks will no longer be synchronized with each other. In fact, the clock that went up into space will be behind the clock that stayed on Earth. And this study has been done multiple times. But as it turns out, the faster you move, the slower time moves for you. Time is relative. This is why it's the theory of relativity. And so we can't really judge time properly because we're always moving. The Earth is orbiting the sun. The Earth is rotating around its own axis. The sun is orbiting around the black hole at the center of the Milky Way galaxy. The Milky Way galaxy is moving in space as well. We're always moving. But if we were to go from Earth to a different planet or a different spot in our galaxy or universe, we might be moving at different speeds, and therefore time would be different in how we experience it. However, a cesium-133 atom is going to, which is radioactive, is going to radiate 9 billion and 200 million or so times every second, what we know a second to be here. So this is where the term atom clock has come from. They use how many times something like a cesium atom radiates, and they use that, since it's exactly that number, they use that to define time. This isn't something that you will be tested on, these ideas, and I really only show for all of these base units how ridiculous it is, because I like to impress upon my students the importance of how science works and how exact things are, and being precise and being accurate. And it's obviously, these definitions are, especially the next ones coming up, are challenging to comprehend, and they're weird and way too picky, but that's what you get with science sometimes. The kilogram will soon be redefined as the mass necessary to make Planck's constant, which we will discuss later in this semester, but not in this lecture itself. And so it'll be the mass necessary to make Planck's constant exactly 6.62606 times 10 to the negative 34th, when expressed in the units of kilogram meters squared per second squared. And you can see there's kilograms in there, and we'll get into what the units of Planck's constant normally are expressed as later, but it's making that value exact. And you can see it's got meters and seconds in there, which are already constant values. So that gives us just the kilogram. The next unit is the ampere, which is the measurement of elementary charge. It's soon to be redefined as exactly 1.60217 times 10 to the negative 19th amp seconds, which is equal to 1 coulomb, the measurement of actual charge. But amp is the base unit, and there's seconds in there, which makes this, again, constant and defined, or definite, because it is based on the second as well, essentially. The Kelvin is going to be redefined soon as well, and it'll be done so by setting the numerical value of the Boltzmann constant exactly equal to that big giant number right there, times 10 to the negative 23rd kilograms meters squared per second squared per Kelvin. Again, everything else in there, the mass, the meters, the seconds, those are definite values which can't change. So if they set Boltzmann constant exactly equal to that, we get just kelvins. We won't go over the Boltzmann constant in class or anything, but if you were to be a chemistry major and take higher levels of chemistry, it would be discussed at some point. The mole is soon to be redefined by fixing the numerical value of Avogadro's constant to exactly 6.022 times 10 to the 23rd per mole. And what that means is, like, if you have 6.022 times 10 to the 23rd atoms, that would equal 1 mole of atoms. And as another point there, 6.022 times 10 to the 23rd is 602 hextillion. So if it's atoms, you have 602 hextillion atoms, which is obviously a number you can't really fathom how many that is. It's so huge. The candela is soon to be redefined by fixing the numerical value of the luminous efficacy of monochromatic radiation of frequency 540 times 10 to the 12th hertz to be exactly 683 seconds to the third power candelas, sterans per square meter per kilogram, which is equal to a lumen per watt. Obviously, the standard candela is really supposed to be the amount of light that a candle gives off, 1 candela, and so that's what that is supposed to be. All right, and then since we're talking about making measurements, we often need to use numbers that are either really, 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 really tiny or really, really, really huge. And it gets very tedious at times to write numbers with that many zeros or that many zeros over there. And so it's easier sometimes to use exponential notation, as seen over there on the right. Much less space taken up when you write those, and the previous couple slides had things written in exponential notation. But you can see all the prefixes over here used to describe those different numbers, where the base unit starts everything. Whoops, I need to undo that. The base unit is the starting point. So if we're talking about meters, for example, we might have 1 meter. All right, I need to just say meters. But if you have 10 meters, you might talk about decameters. And a decameter is 10 meters, and you would write it as 1 dA for deca and m for meters. Or you might have 100 meters, and you could shorten that to 1 hectometer, hm, and so on and so forth. So 1,000 meters is 1 kilometer. You could also say 1,000 meters is equal to 10 to the third meters, and there you get your exponential notation. So those were numbers that were bigger than the base unit. But what about when they're smaller? Well, as you can see there, we have centimeter, or centi, milli, micro, nano, pico, femto, atto, and so they would obviously have all of these with really tiny numbers, and the exponential notation is the key thing there, where they've got numbers to 10 to the negative powers right there. So if I have 0.01 meters, that is going to be equal to 1 centimeter. Centi meaning 100. There's 100 centimeters in 1 meter. Century is 100. You have cents in money. It was 100 cents in a dollar, so centi should give that away. Now the confusing thing is that when we have milli, it has nothing to do with a million. It has everything to do with 1,000. So that's kind of strange to me why it is 1,000 or 1/1,000th of the base unit, not 1/1,000,000th, where the 1/1,000,000th is actually micro, and the symbol for that is that Greek letter mu. So if you have 1 million micrometers, let's see, that's not so good. There you go. That's a Greek letter mu. 1,000 or 1 million micrometers, that will be equal to 1 meter. 1,000 millimeters is equal to 1 meter, and so on and so forth. And then all of the things that we will use in this class, essentially, will be kilo, maybe once deca. No, not deca. We might use, obviously, the base unit of something. We might use deci, centi, milli, micro, maybe nano. So those are the units, the prefixes for them that we will see in this class. All the other stuff are there, and you might be the type of person that reads stuff about science or whatever, and you might see atometers and petameters and stuff like that. Giga is pretty common, meaning a billion of something, but like gigahertz, or how many gigs of RAM or ROM do you have on a computer and stuff like that. That's what that means. So you might see, but we're not going to use in this class. All right, and then there's derived units. These are units of measure that require more than one measurement in order to do it. So for example, area is defined as the length times the width of an object. Essentially, if it's a square, it'd be length times length, but the measurement in its units is meters squared. Even though it's just one type of measurement, both of them being lengths of an object, it's still a derived unit. Volume, length times width times height, is measured in cubic meters if we're using the SI units of measure. Density, we'll get to at the end of this lecture, but density has the symbol, a Greek letter rho, and that is mass divided by volume, which will be measured in kilograms per cubic meter. And the speed is velocity, and that's meters per second, or the distance divided by time, which is meters per second. There we go. So those are all derived units, and most types of units that are out there are all derived units, but they all derive from those 7 SI units. So now we're to the concept of mass and weight. Mass is the amount of matter an object has, or it could be defined as the level of resistance to changes in momentum that an object has, where momentum is given by the equation here, P equals mv, where P is the measure of momentum, the symbol for momentum, m is for mass, and v is for velocity. Think of a speeding train versus a book. They could be moving at the same speed, but which one would you rather hit you, the book or the train? Obviously the book. Actually, really neither, but you'd rather the book hit you if you had to choose between the two, because the train has way more momentum and it's harder to change it because it has so much more mass to it. Now, the mass of an object cannot change. It is what it is. The amount of matter in there is not going to change, because mass can neither be created nor destroyed. Now, the weight of an object can change, though, and this is the force an object exerts due to gravity. Since force is equal to the mass of an object times its acceleration, an object's weight can change if it is changing its acceleration. So, for example, here on Earth, the gravitational force is 9.8, or the gravitational acceleration is 9.8 meters per second squared. But that's the gravitational acceleration is different on the moon or Mars or Venus or anywhere else. So your weight here is what it is, but if you were to go to the moon, where the gravitational forces are much less, your weight decreases, which is why if you see videos of the astronauts on the moon, you see them floating around because they don't weigh as much. And I think they had astronauts hit golf balls on the moon, and they're barely even swinging the golf club because they're constrained by the spacesuit and all, but they were able to hit it much further than a golfer could hit a professional golfer could hit a golf ball here on Earth, because it just doesn't take as much force to move it since there's less gravity. And as a side note, the mass of an object can be determined by taking that weight the F for force and dividing it by the acceleration. So when you step on a balance at home, if you were trying to get the kilograms, how much you weigh in kilograms, all it does is it measures your weight in pounds, essentially, but some metric version of pounds, and then divides it by 9.8 meters per second squared, and you get however many kilograms you weigh. And so really, even though it says mass in kilograms, the machine, the instrument, is still measuring weight first and foremost.